Hello everyone, this is lecture 5 of course PE 645. In the previous lectures, we have introduced the meaning of artificial intelligence and the radiomics workflow, and we mentioned that it consists of 6 or more steps, and we are going to stick with the 6 steps from acquiring the dataset until we reach a high-performance model and explainable model so that we can trust that trained model. We introduce the handcrafted features, first order, second order, and higher order features. The first order deals with the pixel intensities themselves, and the second order deals with the relationship between the current pixel and the neighbors, and higher order features deals with more complex mathematical transformations or filters, and we introduce the purpose of each of them. For the second order features, we introduce GLCM, and we mentioned that we need to construct a co-occurrence matrix, and based on that matrix we can extract the different features such as contrast and homogeneity. Then we created a mini project to extract the different features from a brain MRI dataset with 3 classes. In this lecture we will introduce a new type of a second order features called GLRLM, or gray level run length matrix. If you remember, the GLCM is called gray level co-occurrence matrix, and here has a similar name, gray level and matrix, but instead of co-occurrence we will stick with run length, so it's called the gray level run length matrix, and this tool can be used for texture analysis. And here we are counting the number of gray level runs of different lengths in the image, and the gray level run here means a sequence of consecutive collinear pixels sharing the same gray level value. And we will illustrate the meaning of the sentence or the definition of gray level run after a while. So, to understand the meaning, let's assume that we have an image, and we said let's take the direction of the horizontal one or at angle 0, and we are at a pixel value of 3. So, what to do simply with the GLRLM? We need to find in that direction the number of consecutive sequences of that pixel. So let's assume that the second pixel is 3, the third pixel is 3, and here 3, and then we encounter a pixel of 4, and then another pixel of 4. So simply you will find a sequence of consecutive collinear pixels that share the same value. So here we have 3, and we are moving to that direction, so we will encounter 4 pixels with the same value, which is 3. So in this case we have a run of 4, and 4 here is the count of pixels. Then we have another run, a run of 2 with a value of 4. So the run here simply means if you encounter the same pixel, then count it until you reach a different pixel value, then your run will be the count of the same pixel, which is 3 or 4 that you encountered. As noted with GLCM, we need 3 parameters. Here also we need 3 parameters, the angle, theta, and we define the meaning of angle, whether you need 0 or 45 or 90, and the number of gray levels, n, and also here is discrete intensity levels. So if you have an image with 5 unique values, then n here will be 5, and a new parameter specialized for the gray level run length matrix is called R, which is the maximum run length, and here it's a parameter that also can be calculated automatically, and this reflects what is the maximum number can I reach if all of the pixels have the same value. So simply to determine the R value, we can get the maximum between width and height, because simply if we are dealing with an image like that, so the maximum run will be all of the width or all of the height. So if the width and the height are the same, so it will not make a difference, so either of them. But if you have an image that has a width more than the height or height more than the width, then simply let's make it general. So R here will be determined using the maximum value between the width and the height. And if you are dealing with 3D images or 3D volumes, then you can find the maximum between width and height and depth. So we define the angle, and we can determine automatically the value of n and r. As mentioned with GLCM, we need 2 steps. The first step is to create the co-occurrence matrix, And the second step is to create the features and extract them from the co-occurrence matrix. Similarly here, we need to create the run length matrix, and then based on that matrix, we will calculate the different features. So define first the angle theta, whether we need 0 or 45 or 90 or 135, and then check the matrix and calculate N and R. N here in this case will be 4 because we have 4 unique values, 0, 1, 2, and 3. And R here is the maximum between width and height. The width is 5 and the height is also 5. So R here will be 5. Now we have N and R. Based on these two values, create an empty matrix that will be called the run length matrix with a dimension of N by R, and label the columns to be run followed by a number. Run 1, run 2, run 3, and so on until you reach the maximum run, which is run 5. And for the rows, label them with the gray values from 0 until you reach the maximum value, which is 3 in this case. And this matrix will be initialized by zeros. Now we have an empty matrix. Also, if we have different theta values, such as 45, how can we determine the run or the direction of the run? Simply using the same formula. X target equals X current plus rounding between D multiplied by cosine, and for Y it will be negative round D multiplied by sine. And here we don't have the D or the distance, so we will define the distance in this case by 1. So the formula will be X current plus the rounding of the cosine, and Y target will be Y current minus the rounding of the sine. So if you have 45, then it will be 1 plus the rounding of cosine 45, which is 0.707. The rounding of it will be 1. 1 plus 1 will be 2, which is here in the x direction. And 1 minus the rounding of this value, 1 minus 1 is 0. So the y value will be here. So this is the cell for the direction or the next one. And this would be for 90. 2 plus cosine 90 is 0. 2 plus 0 is 2 if you are here. And 2 minus sine 90, which is 1. 2 minus 1 is 1. So the location of the next will be 2 and 1, which is here. To make it more general, we can follow this pattern because we need to loop on each pixel in that image. So if we have the horizontal, which is theta of 0, we can start from here and move to the direction, and then move to the second row and move to the direction, and so on. And for 90, we can start from here and go down, or start from down and go up and move to the second column, and so on. What about 45 and 135? For the angle 45, we will move to the direction. So we will pick the pixel, and this will be a second, this will be a third, this will be the fourth, and so on. And for 135, we can start from here, then here, then here, or you can simply move also to the direction. So for 45 and 135, you are dealing with the diagonals, the direction or the direction. Now we need to apply that on our example to understand how to fill the run length matrix. We have that matrix, and we said we have n equals 4 and r equals 5, and we are following the direction of angle of 0. So we will start by that pixel and count the number of runs. Simply, we have 1 here, and then if you move to the second pixel, you will find it's 2. So we have only a pixel with a run of 1. So we will fill at the gray level 1, and run of 1, we will fill this place by 1, which was initially had the value of 0. Then move to the second pixel, is 2. Let's check the next pixel, which is 3. So in this case, we have also a gray level of 2 with a run of 1. So we will fill this place by 1. The same for 3. Its next pixel is 2, which is different. So we will fill this value by 1. The same for 2. Its next pixel is 1, which is different. So we will increment the gray level of 2. Instead of 1, it will be 2. The last one is 1, there are no next pixel, so we have a run of 1 at gray level of 1, so we will increment in that field, it will be 2. Move to the second row. Also, you will find 3 with a run of 1, 1 with a run of 1, 2 with a run of 1, 1 with a run of 1, 0 with a run of 1. What about the third row? Here, for 0 and 3, both of them are run of 1. But when you go to 2, here, you will find that the next pixel is 2. So now we have a run of 2 at gray level of 2. So we will move to run of 2 at gray level of 2 and increment that field. And the last pixel is run of 1. For the fourth row, you will see that 1 is followed by 1, is followed by 1, and this means we have a run of 3. So you will go to gray level of 1, run of 3, and increment that field. And also we have at gray level 2, run of 2. So go to that field, run of 2, and increment that field. Do the same for all of the pixels until you reach the end of the matrix. Then this will be your run length matrix. You may mention that how to handle that using Python, because we need something to be generic and automatic to be applied on any matrix. So simply we can follow this approach and apply it in our scripts. How? Simply create a dictionary or a matrix with Boolean values. It's called the scene matrix, and this matrix will include flags if the pixel is seen or not. So if the pixel is seen, so we don't need to calculate it again, because if you remember that I mentioned we need to loop on all of the pixels. So if we are here, there's a second, there's a third, so this will be our run of 3 at gray level of 1. But in the next iteration, you will stop by that pixel. So we need something to remove and eliminate the duplications. So simply by creating that matrix, we will check if we saw that pixel and we counted it in our calculations in the run length matrix, then we will skip it. So if you are here, then check the next pixel, it's 1. It's equal to the current pixel. Then your distance or your run will be 2. But before continuing to the next iteration and finding if the next pixel is also 1, set the flag here to be true. Move to the next pixel. So we have a third run. Don't forget to flag this by true. So now if you move to the next pixel, it has a different value than 1. Then we will stop by that and count the number of pixels. It's 3. So move here, here, and increment that field. We are doing the same, but here we are updating our scene matrix. The reason comes now. We completed that pixel, but now we will move to the next pixel, which is here. Instead of duplicating the run length matrix, we will check that scene matrix. It's true here. So this pixel was seen. So skip it. Move to the next one. This pixel is also seen. Why? Because its value in the scene matrix is true. So we don't need any duplication, so skip it. Move to the next one. We have 2, which was false in the scene matrix. Change it to true. And now we have a gray level 2, a run length of 1. Check its next pixel. It's also 2. So we have run length of 2. But don't forget to update the scene matrix. No more pixels. So update run of 2, gray of 2. That field will be incremented by 1. Now we were here and completed our pixel iteration. Once you move to that pixel, you will find its corresponding value true. So skip it. So the situation here is simple. We will create the scene matrix and we are looping on all of the pixels. Then find the next pixel. If the next pixel is similar value than the current pixel, then continue until you reach a pixel value that's not similar to the current pixel, or you are reaching out of the boundary. Then count all of these pixels, update the run length matrix, and That's it for the current pixel. Once you move to the next pixel, check first if it was seen in the matrix or not. If it was seen in the scene matrix, then skip it. Otherwise, count it. So the scene matrix will help us eliminate the duplications. Based on that, we need to create a script to find our run length matrix automatically based on the input matrix. Open script number 13, GLRLM, run length matrix example. We imported the necessary library, which is NumPy for numerical operations. Then we defined theta. And as we mentioned, we will calculate N and R values automatically. We defined our matrix, and then we converted that matrix to a NumPy array so that we can use the NumPy functions easily. We printed the matrix in front of us. Then we calculated the N as we did with the GLCM by finding the minimum, the maximum, find the difference, and adding 1. And then we calculated the R value, which is the maximum of the shape. And the shape here returns a tuple that has width and height and depth. So the R will be the maximum dimension. Then we converted theta from degrees to radians. After that, we initiated a zero matrix, which will be the run length matrix with a dimension of N by R, and also initiated the C matrix with zeros or falses with the shape of the same matrix. Now we have two matrices and we need to update them. Then we calculated the direction vector, as we mentioned, in which direction we are going to move as a dx and dy. Then we are going to loop on each pixel, and simply in each iteration we will check if that pixel is seen or not. So if the location I and j in the C matrix is 1, which is seen or true, then continue, skip that pixel. Otherwise, set it to true because it's seen. After that, get the current pixel and set the run length to be 1 because you are counting the current pixel in hand. After that, we need to find all the consecutive pixels that has the same value. So we created a third loop here, and in that loop we are simply checking one by one until we reach a different pixel in the value. So we are looping in the direction from the current pixel until we reach the boundaries. For example, I and j here. So this will start from the left to right and here from top to bottom. And we are defining dy and dx because these two values are direction vectors. Now retrieve the pixel which has a value of I plus the d value multiplied by dy, and this simply can be illustrated like that. If I is current is 0 and d is 1 and dy is 1, then simply I plus d multiplied by dy equals 1. So the next pixel will be 1. But in the next iteration, in that case, if I is still 0, d is incremented. In case of the next pixel is similar to the current pixel, then the third pixel location will be 2. So here we have a base direction or a base cell, and we are moving with a specific distance in the direction vector in y and in x. If the current pixel is similar to the target pixel, then simply update the C matrix and increment d by 1. And this is useful because this will eliminate any reductions at the beginning of the iteration later in the next loop. Otherwise, break. And this will happen if this condition isn't achieved, that the current pixel and the target pixel don't have the same value. In that case, update the run length matrix. Go to the current pixel and subtract min A, and this is added for matrices that doesn't start with 0. And because we are indexing from 0 any matrix in Python, we are subtracting here from 1, and then we are incrementing that cell. After completing the whole iteration, we will retrieve the run length matrix. So we can print it. Once you execute the code, you will find the original matrix and the run length matrix. And now you can compare between both of them. Both of them are the same. and the empty cells here, as we mentioned, are zeros, as you notice here. Now, it's your turn. You can pause the video and fill the run length matrix, but instead of angle 0, you have angle 90. And this is the final output. You can compare your output or your run length matrix with this matrix, and then validate that using the code. Now we completed step 1. In step 2, we need to compute the different features. We have multiple features in GLRLM based on the run length matrix. The first couple is short run emphasis and long run emphasis. And here we are measuring the distribution of the runs, here for the short run and here for the long run. The second couple is low gray level run emphasis and high gray level run emphasis. And here we are also focusing and measuring distribution, but for the gray levels, here for the low gray level and here for the high gray level. So these 4 features measure the distribution, and based on their name, you know what they are measuring. Then we have run percentage, and this is the percentage of runs relative to the total number of pixels in the image. Next, we have gray level non-uniformity, and here we are assessing the similarity of gray levels or uniformity of the gray levels, and this also assess the uniformity but for run lengths. So this couple measures and assess the similarity or uniformity here for the gray levels and here for the run lengths. Now we have 7 features. These are the corresponding formulas for these features. Simply, in each, such as short run emphasis, we have 2 loops or 2 summations, and here we have I and J, which are in C's. G is the gray level, R is the run length, P is the probability, as we mentioned with the GLCM, we are calculated the normalized version of the run length, and J is the index, and the position of I and J in the division or multiplication between all of them determines what we are going to measure. So you will say that all of them has a probability with J and I, whether they are in the denominator or multiplied by the P or just as it is, and each combination measures a specific thing, as we noted with the 7 features. For example, to calculate the short run emphasis, we have the formula of summation, and P divided by J square. So this is our run length matrix. So to make it easier for you, we mentioned G are the gray levels, so the index I or the counter I will be for the gray levels. So here set the I values and start from 1, but in Python it will start from 0, so be caution. And also here the R has a counter named J, so here simply start from 1 until you reach 5, and this will help during the calculations. Now we need to define each value here or each probability value here by its corresponding J square, and finally divide that by n. N here is the sum of the matrix, which is here 3 plus 6 plus 3 plus 4 plus 3 plus 1, which is 20. Now we need to calculate B divided by J square. Take each value, divide by the square of 1. 3 divided by 1 square, 6 divided by 1 square, 3 by 1 square, 4 by 1 square. Now here 3 by 2 square, 1 by 3 square. Sum all of that, divide by 20, you will get that value. The same for long run emphasis. Instead of division, we are applying multiplication between the probability and J square. Once you calculate all of that, you will get that value. What about the high gray level run emphasis? We are multiplying by the I square. We have a probability. Instead of dealing with J, now we are dealing with I. So once you find a gray level in the definition, deal with I. Once you find run length in the definition, deal with J. So here 3 multiplied by 1 square, 6 multiplied by 2 square, 1 multiplied by 2 square, 3 multiplied by 3 square, 3 multiplied by 3 square, and 4 multiplied by 4 square. Sum all of that, divide by 20, you will find that value. Now we need to code a script to calculate all of these features automatically based on the calculated run length matrix. Now, open code number 14, GLRLM features example. You will find that we imported NumPy for the numerical operations, and we imported the helper file or the helper functions. And inside that helper functions, we encapsulated the calculation of the run length into a function that can be used with different codes. And in that function, we accept the matrix, theta, and the two flags is normalized and ignore zeros, and by default, both of them are true. And here inside the function, we did the same, defined n and r, defined the matrix and C matrix, and calculated the direction. And if you notice, we kept them to be positive, and only dx will be swapped to be negative in case we encounter the angles 45 and 135, and they are written like that to be dynamic for all of the angles. Then we created two inner loops as we did, skipped if the pixel is processed and seen, exchange the flag, get the current pixel, set the distance or the run length to be 1, create a loop and count the number of run lengths for the current pixel. If you are ignoring zeros or the current pixel is 0, then continue, ignore it. Otherwise, fill the matrix and update it by incrementing the cell. If you need to apply normalization, then divide by the summation and add here a very small value. It's called epsilon. After that, return the matrix. So we can use that function here, and based on the returned run length matrix, we can calculate the different features. Define theta, define the matrix, and then execute that function, which requires the matrix, which is A, which is converted here to NumPy array. Then we are passing the angle in radians after converting it using the radians function. Don't apply normalization for our example, and don't ignore zeros for our example here, because we need to validate our calculations. But with images and medical images, we will set this by true and this by true. Then we need to calculate the total sum of the matrix, which will be used in our divisions. And to avoid the duplication of the variables, we will rename this to be run length n, because we have another n value, and this reflects the distinct unique values. So to avoid any duplications or overriding each other, we will keep this by n, and this will be run length n. Now let's create a different feed. Simply, for the short run emphasis, we need to get each value and divide it by the square. So simply, if we can get each row and divide it pixel-wise on that sequence and do that for all of the others and then sum them together, we can retrieve the same value. So here we got the matrix and divided it pixel-wise on the sequence squared from 1 to r plus 1. As we noted, to take care that we are starting here from 1, but in Python starts from 0. So we are incrementing here 1 and starting from 1. After calculating the summation, we are dividing by the n value, which is the sum. For the long run emphasis, instead of division, we are applying multiplication. And for the gray level and run length non-uniformity values, which is here and here, we need simply to square each column and each row and then do the summation. So here we are squaring the summation of the rows and columns individually and then summing all of the values together. After that, we are dividing by the n value. For the RP or the run percentage, we are dividing the summation by the total number of pixels in the image. So we will divide the n value by the total number of pixels in the image by simply applying the product between the different dimensions. So if it's 5 by 5, here we will get 25. Finally, the low gray level run emphasis and high gray level run emphasis, we need to do the same division and multiplication, but instead of the j values, we need to apply that on the I values. And here we can do that simply by creating a sequence and square it from 1 to n plus 1, and the division will be for the low gray level and the multiplication will be for the high gray level. We calculated the different features. Now we can print them on the command window after rounding each of them to 4 decimal points. And this will be the corresponding out. You can now compare the short run emphasis 0.84, which is here, and the long run emphasis 1.85 like here, and the high gray level run emphasis 7.45, which is here. You can calculate also other features and validate your output. Similar to what we did with GLCM, to replace the matrix with the cropped ROI, we need now to do the same. We need to read the image, the mask, and find the ROI and apply cropping to get the cropped ROI, and then calculate the run length from that cropped version and calculate the different features from them. So go to Code 15 GLRLM features for 2D. We imported the packages OS for file operations, CV2 for image processing, NumPy for numerical operations, and the helper functions file. As we did with GLCM, we read the image and corresponding mask. It checked that both of them exist, read both of them in the gray level, applied bitwise and created the cropped version. It checked if that mask is not empty or that cropped version is not empty, because we don't need to deal with black images. Then defined theta, defined theta red, which is the conversion from degrees to radians, executed that function and set that flag to true and that flag to true for ignore zeros and apply normalization. Now we have run length matrix. We created another function that you will find it in the helper file, which is here, that accepts the run length and the original image and calculates the different features as we did from a minute and returns all of these features as a dictionary. We can now get these features and execute the code and get these features to be printed and rounded to 4 decimal places. After executing the code, you will find the following output. You can change the angle and validate the output. Also, we need to do that on 3D volumes. We have images, volume, and the corresponding mask's volume. So we will apply, as we did with the GLCM, the spherical coordinates to get x, y, and z. And d here will be equal to 1. And also we will take care of the padding, as we mentioned that not all of the images share the same width and height after the cropping. So we will check the maximum width, maximum height, and unify the shapes by adding padding around the image to keep it in the center. Now go to the last code, lecture 16, GLRLM feature for 3D. We imported OS, CV2, and NumPy again, and the helper functions file. And we added in that file the function that we created earlier that's called read volume, that accepts the paths and returns the volume cropped. After cropping each of the images, apply padding and unifying the width and height so that we can use that function in any of our future scripts. We define the paths for the image's volume and masks. We defined theta and converted it to radians, read the volume and got the volume cropped, and then applied that to two functions, one to calculate the run length for 3D and another to calculate the 3D features. This is the first function that accepts the volume instead of the image. Theta is norm and ignore zeros. And here we will do the same, but instead of using only dx and dy, we'll use dx, dy, and dz. We calculated n and r, created the run length and seam matrix, created the direction vectors, and instead of 2 loops, we created 3 loops. We checked if it's seen, skip it, otherwise update. And instead of looping on just 2 boundaries in each direction, we are looping in 3 directions. So you will find here 6 conditions instead of 4. And here we will check the current value as we did with the 2D version. But here we have 3 dimensions, I, j, and k. Then if you need to ignore zeros and the current value is 0, then ignore it and continue. Update the run length matrix. Check if we need to apply normalization. If so, normalize by dividing by the summation plus a small value is called epsilon, then return the run length matrix. Now we got the run length matrix, and if you notice, the run length matrix has a dimension of n by r, and instead of creating a special function for 3D to calculate the features. We can use the same function as we did with the 2D, which to calculate the GLRM features by passing the run length matrix and the volume, and it will start to calculate the different features as we illustrated from a while, and then return all of these features as a dictionary. Then we can print all of these features on the command window rounded to 4 decimal points. With that said, in this lecture, we have covered the GLRM matrix and the corresponding features, and we mentioned that to extract features using GLRM technique, you need 2 steps. The first step to create the run length matrix, then to extract the different features such as short run emphasis and long run emphasis.